This lecture is over the chain rule and the general power rule. So if you've read the book, you kind of see that we've actually already been dealing with the chain rule. The book just called it back in chapter 2, no, 1, chapter 1, we talked about the general power rule, which really is just a case of the chain rule. And when we get to, we're going to start talking about logarithms and exponential functions soon. So the chain rule is really going to come into play then, and you've already been using it. So that's the great thing. So let's just write down what the chain rule is. And then I'm just going to do a couple examples for you and talk about some different notation. And it should be hopefully somewhat short and sweet. So here's what the chain rule says. The chain rule all has to do with a composition of functions. And we talked about this when we talked about the general power rule. So if I have a composition of functions, if you remember from, like college algebra, is where I have one function inside another function. And what the chain rule says is you need to take the derivative of the outside function, leaving the inside function as it is. So basically what we want to know is how is this function changing with respect to the outside function? And then we need to multiply by the derivative of the inside. Because remember what the derivative gives us? The derivative gives us a rate of change. So what this is taking into account, the chain rule is taking into account the rate at which my outside function is changing times the rate at which my inside function is changing. So for example, we've actually already done this before. I'm going to call this a different function. Let's say h of x. And let's say we have 3x squared plus 1 all to the 5th power. So let me show you kind of what this means by the chain rule. So if you look at this, h of x can actually be written as f of g of x, where what is f? F of x would be my outside function, which would be x to the 5th, and g of x would be my inside function, which in this case would be 3x squared plus 1. So if you remember from, college algebra, if I wanted some notation here, the fog, or f composed with g, you might see that notation, or g of x. Remember what that was? This says everywhere I see an x and f, I'm going to put the entire function g. So this g is going to be replacing every single x I see in the function of f. So that's what this is saying right here. So look at what the chain rule tells us to do. The chain rule tells us to take the derivative of f and then evaluate it at g times the derivative of g primed. So if the derivative of g prime times g prime. So if I wanted to take h prime, so let's look at how this would work. This would be f primed of g of x times the derivative of g. So f primed of x, what would f primed of x be? Well, f primed of x, right, in this case is 5x to the 4th, which is pretty easy to see. So what would f primed of g of x be? Well, that just means everywhere I see an x, I am going to put g of x. Okay, that's all that's saying, right? So I've just taken the derivative and I've evaluated this x at my function g. And we see this with the power rule. We already know this, right? So I bring the 5 down, I leave the inside, I take 1 away, and then it says to multiply by the derivative of g, which clearly the derivative of g is just 6x. And so my final answer here, so I hope this is nothing super new when it comes to actually applying the chain rule for right now. Really, the big deal of applying the chain rule in this case is just going to be basically doing the general power rule, because that's the same thing. Okay, so I hope that kind of makes sense. The big part of this section that can be somewhat confusing is we'll write this down as a theorem. I'm not going to prove it, but we'll just talk about it. Here's the big part with this section that can be a little bit tricky, is this other notation for the chain rule. So let's say that I have some y, and let's say that this function y is a composition, okay? And what I'm going to do is I'm going to let u equal this function g of x, Okay, so if I look at y, and if I want to take the derivative of y, so y equals f of g of x, y then is going to be some function of u. I'm just defining u to be the inside function. Okay, so if I want to find, so here's what my theorem says. Let's just write this down really quick. If I want to find the derivative of y with respect to x, right, what I need to do is I need to take the derivative of my outside function. So that means I'm going to take the derivative of y with respect to u, and then I multiply by the derivative of the inside function. And this inside function, this u right here, is a function of x. So I want to show you an example of this because this notation can be a little bit tricky. So look at what this is saying. dy dx, take the derivative of the function with respect to u, then multiply by the derivative of u with respect to x. This is the multiplication of the inside function. So let me do an example of this for you. So let's let y equal, nope, that's not what I wanted. I want 4 times the square root of u plus 2u squared, where u is equal to 5x minus 1. So I want to look at 2 ways of doing this, okay? So look at how this is a composition. If I take this u is a function of x, that's my g of x, and I plug it in for each u here, I would get a composition of functions. So let's look at what this theorem right here tells me to do. The first one, right, this first part right here says this is the derivative of y with respect to, we say with respect to u, and then this guy right here is the derivative of u with respect to x, okay? So this is the chain rule. Again, oh, I don't know if I ever said this. This is just another notation, other notation for the chain rule. So let's, oh, I messed that up. So let's look at what we want to find here. I guess I'm going to have to get rid of all of that, but that's okay. All right, so I want to find, let's say I want to find dy dx, okay? Whoops, sorry about that. So I want to find dy dx, because look at what I have though. I have y is a function of u and u is a function of x, but I want to find dy dx, okay? And I don't know why this isn't working, probably because I was on eraser. So if I want to find the derivative of y with respect to x, even though y is a function of u, I'm going to take dy du times du dx. Okay, so what would dy du be? Well, this would be 4 times the derivative with respect to u. So what I've done here is I've just taken the derivative of this guy with respect to u. And then what does it say to multiply by? This is the derivative of the inside function. So I would multiply by 5. Okay, so dy dx, so if I want dy dx, I want my final answer to be in terms of x. So I'm going to just clean this up a little bit. This is 2, actually let's half of 4 is 2, and then that negative 1/2 means I'm on the bottom, plus 4u all times 5. And then look at what my final answer would be. I would actually take this 5x minus 1 and plug it in for every u here. Because if I wanted the derivative of y with respect to x, I need to make sure that my final answer here is in terms of x. I'm also going to take that 5 through just for the fun of it. So I would get square root of 5x minus 1 on the bottom plus 4 times 5x minus 1. Okay, so that's, oh, not 4, excuse me. If I'm going to multiply that 5 through, I got to commit, right? Oh my goodness. This is, you would think after like 9 weeks of using this program, I would actually be able to do this well. If I take that 5 through, and this is probably good enough. I could get a common denominator, but because this isn't a square root, you know, nothing is really going to cancel or anything really nice is going to happen there. So this would be it. This would be my dy dx. Now, I want you to see if we had, this is just one way of doing the chain rule. If I had actually made the substitution first, if I had actually put in u, right, and I actually just rewrote y in terms of u. Okay, I could actually just use the general power rule and take the derivative of this. I would get 4 times 1/2, which is 2, leave the inside, take 1 away, right, times the derivative of the inside. Now I'm just using the general power rule, which again, the general power rule is really just the chain rule. And if you notice here, if I clean this up a little bit, I would get the same thing. So I hope that kind of makes sense. This notation can be a little bit tricky. So make sure you're looking at the fun sheet. Make sure you're reading all the examples in the book because this notation can be a little bit tricky. I want to do one more example with this notation. Well, actually, we'll kind of do 2 more examples with this notation, and then we'll call it good. So the next example I'd like to do for you is let's find, I want to find dy dt evaluated at t naught, which we are going to set equal to 1, if or for, here's what y is going to be. Y is going to be the function x plus 1 all over 2x minus 1, which notice y is a function of x, and look at what we're asking for. We're asking for the derivative of y with respect to t. So that must imply that x is a function of t. So I don't always have to have u's. So look at what this is saying. If we think of t as time, x is changing with respect to time, and then y is changing with respect to x. So I could find the way that y is changing with respect to time if I think of this as a composition. So if I want dy dt, look at what we're going to have to do. Based on that notation from the last example, what is y a function of? Y is a function of x, so what I would need to do is to first take the derivative of y with respect to x, and then multiply by the derivative of x with respect to t. And if you notice, these dx's kind of cancel out. They don't actually cancel out. These are what we call differentials in calculus. So they don't actually cancel out, but what they do for us is they tell us how we're going to evaluate this. And then, of course, I'm going to evaluate it all when t is 1. So let's look at taking this derivative. So if I look at y, I'm going to do the quotient rule, right? So the quotient rule tells me down, d up, so derivative of the top, minus up, d down, the derivative of the bottom is 2, all over down, down. I hope you're starting to get comfortable with the quotient rule. So there's my derivative of y with respect to x, and then what is the derivative of x with respect to t? It looks like that would be 8t. Okay, now the great thing is I don't want to plug this 4t squared into all of this. What I'm hoping to do is to be able to do this without having to actually plug that all in. So on the top here, let's simplify. I'll just use a different color. I would get 2x minus 1, and now I'm going to take the negative and the 2 through. So that'd be minus 2x minus 2. And on the bottom, I'm not going to simplify the bottom. But on the top here, I see that these guys cancel. And it looks like I just get negative 3 over 2x minus 1, quantity squared, times 8t. And now this is dy dt. Now I know it doesn't look like it's dy dt because we have x's in there, but technically this is dy dt, and I could plug this 4t squared in for x. But what do I actually want to find? I want to evaluate this sucker when t equals 1. So I need to do a little bit of work. What is x when t is 1? Well, that'd be 4 times 1 squared, which is 4. So the reason I need that is because this guy right here, when t is 1, is going to replace this x down here. Okay, so when t is 1, what is x? X is 4. So on the bottom here, I would have 2 times 4 minus 1 squared. And then obviously when t is 1, t is 1. So that would be just 8 times 1. And so what do we get? We get negative 3 all over, this is 49, I think, times 8. So my final answer, so if you notice, sometimes the chain rule is helpful for us. If we want to find a derivative that would, if we actually plugged 4t squared into this, you can see how maybe my quotient rule could get a little bit complicated. So I hope that makes sense. I want to do one more example. And I want to do an example that has to do with some business. So this is going to be a bit of writing. So I'm going to pause the video and write this, and then you can pause it and then write it as well. Okay, so I bet that's a little weird to watch. So look at what we have here. We have a store estimates that its cost when selling X lamps per day is given by the function C of X equals 40X plus 3, and we'll just say this is in dollars. If daily sales are rising at a rate of 3 lamps per day, how fast is the cost rising? So here's what we want. Again, my want or my objective. What do I want? I want to know how fast is the cost rising? So if you think about that, let's think about what the units would be on that. If I'm thinking about cost rising, I'm asking how fast, dollars per day, right? So what that's asking, how fast that's rising, that's asking the rate of change of my cost with respect to time. And when do we want to know that? When we know that the rate of change of my lamps with respect to time is 3. Look at this right here. This is saying the rate of 3 lamps per day. So X, remember, that's lamps. And T, I'm going to let T be day. And then remember, the D's in front imply a rate of change. So this is the rate of change of my lamps per day. So that is going to be 3 lamps per day. So notice, what do I know? If I know from the chain rule, right? dc dt, the rate of change of my cost with respect to time. Look at my cost. My cost, right, is a function of x. So I want dc dx, it's a rate of change of my cost with respect to the lamps, times the rate at which my lamps are changing with respect to time, right? My outside function kind of is the x. My inside function is x with respect to t. Now the difference with this is I don't actually have a function x equals, something with a t squared plus 2t or something. I don't have any of that, right? But what I do know is that dx dt is 3. So I actually don't need to know the function for x with respect to time to be able to complete this problem. So think about this again. What is this guy here? This is, let's write this down really quick, because again, half the battle is understanding what this means. This right here is the rate of change of cost, right? That's what that C is on top, with respect to whatever is on the bottom, time. This guy here is my rate of change, I'm getting a little lazy here, of cost with respect to lamps, right? So this would be the cost per lamp sold. And this guy right here is the rate of change of lamps with respect to time. Okay, I hope that makes sense. All right, so let's look at how we would actually solve this. All right, so what I need to find, and it looks like I don't have enough information, but I actually do by the nature of what the cost function is. dc dx, what is the derivative of this with respect to x? It is 40. We know, because this is linear, that my cost is changing with respect to lamps by 40 lamps, or $40, excuse me, per lamp. Okay, that's what that's saying. Cost with respect to lamps, so that's $40 per lamp. Okay, for every lamp I sell, my cost increased by $40. So that's my dx/dc times what is dx/dt. That would be the $3. Let's put this, let me give you some units on this. So this is $40 per lamp, right? That's what that dc/dx means. What is the dx/dt? This is the rate of change of lamps with respect to time. This is 3 lamps per day, right? That's what they tell us, per day. So if you notice, look at what cancels. If I look at my units, my lamps cancel. And what is my final answer? What is the rate of change of my cost, or how fast is the cost rising? It's rising at $120 per day if I'm increasing my sales by 3 lamps per day. And then you, of course, would write that in a sentence. All right, go work on the homework and let me know if you have any questions.